evening, ladies and gentlemen. Welcome to a night where science meets curiosity and where the vastness of the universe brings us closer together. I am Tishaka De Silva, and it is an absolute pleasure to be your host for this very special occasion, the first session of Meissa 2.0, proudly organized by the Astronomical Society of the University of Colombo. Tonight, we embark on a journey beyond stars and galaxies into one of the most fascinating frontiers of modern science, astrobiology. The universe is vast, but the search for life brings us even closer. Today, we are reminded that in our quest to understand what lies beyond, we also discover more about ourselves, our origins, and our place in the cosmos. It is with great honor and excitement that we introduce our distinguished speaker tonight, Mr. Sathira Deegala, a graduate in Biochemistry and Molecular Biology, and most notably, the former Assistant Secretary of the Astronomical Society of the University of Colombo. Mr. Sathira Deegala is no stranger to the wonders of space and the mysteries of life. Tonight, he will guide us through the captivating realm of astronomy and astrobiology, where biology meets astronomy in the search for life beyond Earth. So, sit back, stay curious, and get ready to explore the possibility of life beyond our world. Without any further ado, please join me in warmly welcoming Mr. Sathira Deegala. Sir, the stage is yours.
Thank you, Tisha. Yeah, I will go straight to the lecture then. You introduced me very well, I think. So no need of further introductions. I will move on to the lecture. I hope you guys can hear me clearly.
Yes, sir.
Okay. So there's like a storm going on and the connection is not so stable. So I will switch off my video for now and I'll share my screen. So please let me know if my connection has some problems or if I'm lagging. Otherwise, I will be continuing with my slides. So today we are talking about astrobiology. I thought about giving a very brief introduction to astrobiology, the very basics of astrobiology. මම ඇස්ට්‍රෝබයොලොජි ගැන කතා කරන්නම්. මම හිතන්නේ සිංහල ඉංග්‍රීසි දෙකම යන වැඩිපුර පොඩක් ඉංග්‍රීසි වේවි. If you have any questions, you can ask. You can type in the chat. I will try to answer. So මම ගැන පොඩ්ඩක් කිව්වොත් තිශාක කිව්වා වගේ මම biochemistry molecular biology graduate කෙනෙක්. මම astrobiology expert කෙනෙක් නෙවෙයි, but මම තනියෙන් ඉගෙනගෙන තනියෙන් කියවලා ඉගෙනගත්ත දේවල් වලින් introduction එකක් මෙතන ඉන්න අලුත් astronomersලට astrobiologistsලට future astrobiologistsලට starting points ටිකක් දෙන්න. astrobiology ඉගෙන ගන්න පටන් ගැන්මක් දෙන්න තමයි මගේ බලාපොරොත්තුව. So let's see how it goes. So astrobiology, to start off my lecture, I will start with a quote by Sir Arthur C. Clarke. Either we are alone in the universe or we are not, and both are equally terrifying. So අපි universe එකේ තනියෙන් ඉන්න පුළුවන් or අපි තනියෙන් නොවෙන්න පුළුවන්. ඒ මම හිතන්නේ concept දෙකම අපි හිතුවොත් equally terrifying, ටිකක් බය හිතෙන concept එකක්. astrobiology කියන විෂය ගත්තට පස්සේ ලෝකය දන්නවා. ඒගොල්ලෝ දන්න විදියට ගොඩක් වෙලාට ලෝකය දන්න විදියට ඇස්ට්‍රෝබයොලොජි වලින් අපි ආන්සර් කරන්න හදන්නේ මේ ප්‍රශ්නයට මේ possibilities දෙකෙන් මොකක්ද තියෙන්නේ කියලා හොයන එක තමයි අපි සාමාන්‍යයෙන් ඇස්ට්‍රෝබයොලොජි කියලා දාන්නේ. හැබැයි අපි ඇස්ට්‍රෝබයොලොජිස්ට්ලා විදියට ප්‍රොපර් ඇස්ට්‍රෝබයොලොජිස්ට්ලා විදියට මේ ප්‍රශ්නේ ටිකක් එළියට ගිහිල්ලා බොහොම බේසික්ස් වලින් පටන් ගන්න ඕන. එහෙම ගත්තොත් ඉස්සර ඇස්ට්‍රොනොමි කියන සබ්ජෙක්ට් එක තාරකා විද්‍යාව කියන සබ්ජෙක්ට් එක මුල් වෙලා තිබ්බේ අහසේ තියෙන වස්තුන් ගැන හොයලා බලන එක. We wanted to discover the wonders of the space. We were curious about how stars works, about galaxies and everything. But today we have gone beyond that. We understand the space, the universe up to some extent. So now we are trying to habilitate. We are trying to find a possibility of life around, not around the Earth, away from Earth, out of the Earth. So space explorations, all the space programs, all those things are now based on finding the possibility of life outside of Earth. So අපට කියන්න පුළුවන් දැන් තියෙන astronomy කියන subject එක බේස් වෙලා තියෙන්නේ මේ ඇස්ට්‍රෝබයොලොජි කියන එක මුල් කරගෙන තමයි ඇස්ට්‍රොනොමි කියන සබ්ජෙක්ට් එක මේ දවස්වල 21 වෙනි සතවර්ෂයේ ව්‍යාප්ත වෙමින් පවතින. අපි මගේ ලෙක්චර් එක මම බොහොම බේසික්ස් වලට සීමා කරනවා, ලොකු ඒවට යන්නේ නැහැ. ඇස්ට්‍රෝබයොලොජි ගත්තට පස්සේ මට වැදගත්ම දේ මේ ලෙක්චර් එකෙන් ඕන ඔයගොල්ලන්ට ඇස්ට්‍රෝබයොලොජිස්ට්ලා විදියට හිතන්න පොඩ්ඩක් පොයින්ට්ස් ටිකක් දෙන්න. මොකද ඇස්ට්‍රෝබයොලොජි කියවම ගොඩක් අය මං හිතන්නේ දැන් තියෙන සෝෂල් මීඩියා Google ඉන්ටර්නෙට් එක පොඩ්ඩක් tends to deviate from the core astrobiology පොඩ්ඩක් ඇහුවාම ආස හිතෙන දේවල් පොඩ්ඩක් ඉන්ට්‍රෙස්ටිං දේවල් වලටම පොඩ්ඩක් යොමු වෙන්න බලනවා. කෝ ඇස්ට්‍රෝබයොලොජි කියන එක ඇත්තටම මම හිතන්නේ ගොඩක් කට්ටිය හරියට තේරුම් අරගෙන නැහැ. ඒකින්ද මම බලාපොරොත්තු වෙනවා කෝ ඇස්ට්‍රෝබයොලොජි වලින් ටිකක් දෙන්න ඔයගොල්ලන්ට. එතන ඉඳන් ඔයගොල්ලන්ට මේ ලෙක්චර් එකෙන් පස්සේ මගේ පොයින්ට්ස් එක්ක ඔයගොල්ලෝ රිෆර් කළා ඔයගොල්ලන්ගේ ඕන් ජර්නි එක පටන් ගන්න පුළුවන්. ඒක තමයි මගේ බලාපොරොත්තුව. So let's start with the topics. So I will discuss what is astrobiology and I'll try to define life. And we'll talk about the habitability of a planet, which is the major fundamental of astrobiology as a subject, as a thing. And then we will talk about evolution of life, extraterrestrial life, and intelligent life. If we have time, we can discuss a little bit. And I will ask some questions. I hope you can at least send me answers in the text box in the chat. So let's see how it goes. So start with the lecture. I think very first thing we have to discuss as an introduction is what is astrobiology. Anyone? Any guesses? I hope everyone can understand what I'm saying. ප්‍රශ්න තියෙනවා නම් අහන්න, තේරෙන්නේ නැත්නම් terms තේරෙන්නේ නැත්නම් අහන්න. So what is astrobiology? So there are two spaces. What do you think comes into these spaces? Anyone can define astrobiology? Yes. So I have an answer. Study of life on Earth, out of Earth. Okay. Study of life out of Earth. Good answer. Any other answers? So since we are a bit late already, I'll continue, I guess. So this the old astrobiology, which is called exobiology. Study of life on exoplanets, yes. So exobiology. So the astrobiology, I think most people know, is actually not astrobiology. It's exobiology. Exobiology is the subject where we study life in space. So exobiology has four main subjects, four main uh, subjects that forms exobiology, which is planetary science, origin of life science, life studies, exoplanetary studies, and search for extraterrestrial intelligence. So this is the core, like the astrobiology, which is popular among everyone. But this is not really astrobiology. We call this exobiology because the thing is, uh, this exobiology doesn't have a real basis. It doesn't study life. It doesn't know where to look, what to look. It's just looking for life out of the earth blindly. So recently, uh, at the late 20th century, beginning of the 21st century, we have a new subject called astrobiology or xenobiology. So astrobiology is the subject where we study life on earth and we relate that life to find life beyond Earth. So astrobiology, the basis is not just life away from Earth, out of Earth. It's actually based on study of life on Earth. So astrobiology is a collaboration of a lot of subjects, not just a limited area. It has astronomy, planetary and earth sciences, chemistry, biology, biochemistry, molecular biology, and evolutionary biology. So we have to understand what life is to look for life away from Earth, out of Earth. So astrobiology tries to answer that question by studying life on Earth first. So that is the major thing about astrobiology. Everyone thinks, okay, so astrobiology is very fancy, a fancy name. It's about aliens, extraterrestrial life. But no, astrobiology can be a little bit boring. It's about life on Earth at first. So as astrobiologists around the Earth, around the world, are still trying to understand what life on Earth is before going on to life in space. There are missions, but the major goal of astrobiologists is to define life on Earth. So there are different subjects: biology, biochemistry, molecular biology. So biochemistry and molecular biology is where I come for astrobiology as a subject. So I'll go from astrobiology to life. So astrobiology, we try to define life on Earth. So what is life? Can someone define what life is? Any answers in the chat? You can, yeah, I'll give you 2 minutes because I need a lot of, I have a lot of things to discuss with you. So any answers? What do you think? Simple answers. What is life? This is the central question of astrobiology. What is life? So I am not getting any answers. Yes, it will be easier if you can put it in the chat. I know there's a storm going on. The connections are not the best today. The existence of species, yes, can be. Any other answers? Yeah, you can put it in the chat. I will continue with my lecture. So, existence of an individual or an animal, yes. So how do you define individually, define an animal? That is the problem. So life, even as biologists, is a very big question because uh, starting with this question, we don't have an answer. We can't define what life is, and we don't have a definite answer so far. So the starting point, the very starting point of astrobiology is a question. So we try to look for life outside of Earth, but before that, we need to define life on Earth, and that is a question itself. So as biologists, it is difficult to define what life is. biologists have difficulty agreeing what constitute as life. So it's a question, no answers. The only thing that we can do is try to distinguish life from non-living matter. So we say life is the condition that distinguishes animals and plants from inorganic matter, including the capacity for growth, reproduction, functional activity, and continual change preceding death. But the problem is we don't only consider animals and plants to be life. There are bacteria, there are protozoa, there are algae, fungus, there is a lot of things that we consider to be alive. So it's still not a very good way to define what life is. So for that, we have 7 characteristics: order and organization, metabolism, growth and development, irritability and coordination, adaptation, reproduction, and heredity and evolution. So we say irritability and coordination. Irritability is the ability to respond to stimuli. Irritability කියන්නේ අපිට එළියෙන් තියෙන සිග්නල් එකකට රෙස්පොන්ඩ් කරන්න පුළුවන් හැකියාව. Metabolism, I think you can, it's not that complicated, these things. So 7 characteristics, we say if something has all these 7 characteristics, that is life. So only life can have all these 7 characteristics. Non-living things cannot have all 7 characteristics. Non-living things can have 6, 5, 4, can be any number, but not all 7 things. All life should have all 7 characteristics. So the start of astrobiology itself is a big question. It's difficult to define. So yeah, that's how this subject works. That's why we need a lot of subjects to keep astrobiology going on. So I think up to this point, you can see we are starting in a bit of a bad way. But let's see how it goes. Let's see if it becomes better. So life, අපට පොඩ්ඩක් life එක define කරගන්න පුළුවන්. Then for astronomy, we can't actually look for these characters outside of Earth. So let's say we have defined life like this, but we can't look for all these characters outside of Earth. Things are too far away, though things are in astronomical scales. We can't look for these characters. So we try to find some fundamentals of Earth-like life. So astrobiology starts looking for life outside of Earth by defining Earth-like life. So astrobiologists look for life outside of Earth. They look for Earth-like life, not just life in general. So all these 7 characters that I'm showed you are characters of Earth-like life. So to look outside of the Earth, as I said, we can't look for these characters. These are in astronomical scales. So we look for 3 fundamentals that define Earth-like life. So Earth-like life is carbon-based. It's solvent-based and it's solar energy-based. So Earth-like life is built with carbon. The building blocks of life is carbon. In addition to carbon, hydrogen and oxygen are also there. So the building blocks of life is carbon as an element. So these building blocks are together, communicate together, function together by the help of a solvent. And the solvent in our bodies, in the body of all living organisms on Earth, is water. So carbon-based, solvent-based, and we extract energy. We need energy to make these building blocks, and the processes keep going to continue these processes. So this energy is taken from sun's energy, solar energy, through the process of photosynthesis. ප්‍රභා සංශ්ලේෂණයෙන් ගස් ප්‍රභා සංශ්ලේෂණය කළ හදන sugars, කෑම වලින් තමයි all life on Earth depends on these things. So we have 3 fundamentals to look at. So we are on a bit of a good starting point, even if we can't define life itself. So as astrobiologists, we can look for these characters outside of Earth to find life outside of Earth. So I'll talk about a little bit throughout this lecture about the possibility of finding life outside of the Earth. like the most common concept is like there's a good possibility that life is out there in the galaxy itself. So let's talk about that. So I think we are at a good point to start talking about that because we have three fundamental points to look for outside of Earth. So looking at these characters, we define a habitable zone for a planetary system. So a habitable zone is made up of the conditions and characteristics of an environment that make it suitable and conducive to support life, conducive life එක පවත්වාගෙන යන්න හැකියාවක් තියෙන area එකට අපි කියනවා habitable zone කියලා solar system එකක planetary system එකක. So Abhigatot, habitable zone, I think it's a very popular concept, a very popular model in astrobiology. It is like the very basic of astrobiology. So I will go into a little bit of detail into the habitable zone. So as astrobiologist, as young scientist, you have to know things properly. So habitable zone is the region around a star where liquid water can exist. So ද්‍රව ජලය ප්ලැනට් එකක ග්‍රහලෝකයක මතු පිට ද්‍රව ජලය පැවැත්තිය හැකි ඒරියා එකට අපි කියනවා තරුවකින් තියෙන ඒරියා එකට කියනවා habitable zone කියලා. The region around the star where liquid water can exist is the habitable zone. So this depends on two factors, which is insolation and escape velocity. So අපි කතා කරොත් fundamentals ගැන carbon based, solvent based, energy based, carbon based is අපි එක පොඩ්ඩක් පැත්තකින් තියමු. Solvent and energy is what we are looking for in a habitable zone. So අපි බලනවා liquid water තියෙන්න පුළුවන් තැන සහ enough solar radiation හම්බෙන්න පුළුවන් තැන. Insolation is the amount of solar radiation that reaches the surface. So insolation covers the requirement of solar radiation. Insolation is the amount of solar radiation that reaches the surface. Escape velocity, I think you guys might know. Escape velocity, we call සිංහලෙන් කියන වියෝග ප්‍රවේගය කියලා, is the minimal velocity that is needed to eject something from a planet's gravity. So habitable zone is defined around the sun's radiation and the atmosphere of a planet. So to have liquid water on a surface of a planet, there should be an atmosphere. So atmosphere එකක් තියෙනවා නම්, heavy enough atmosphere, good enough atmosphere එකක් තියෙනවා නම්, liquid water තියෙන්න පුළුවන් planet එකක surface එකක. And මේ atmosphere එකක් තියෙන එක, atmosphere is just basically a cover of gas. It's a envelope of gas around a planet. So මේ gases planet එකක් වටේ තියාගන්න පුළුවන් හැකියාව depend වෙන්නේ planet එකේ escape velocity මත. So habitable zone is defined by the insolation and escape velocity, and it depends, as in general, habitable zone depends from the distance from the star. So as you can see in this diagram, you can see cool stars have a habitable zone closer to the star itself. Hot stars have a habitable zone a little bit away, not little bit away, very far away from the star. So this is the basic idea: liquid water, atmosphere, and the distance from the star. But as you can see, hotter stars have a can be broader and a far away habitable zone located a bit far away from the star. Cooler stars have a narrower and habitable zone located very close to the star. So that is the basic idea, very simple idea, not that complicated, until you go to the astrobiological definitions of habitable zone. So this is actually supported by some climate models, solar system, climate of the solar system, and astrophysicists, astrobiologists, and climatologists got together to define this habitable zone. The astrobiological definitions of habitable zone is a little bit complicated. So Here it shows a basic habitable. The range is showing a basic habitable zone. As you can see in the diagram, there are some labeled labels called runaway greenhouse, moist greenhouse, maximum greenhouse, and there are different sizes, the temperatures of stars, sizes of stars, and different exoplanets and the planets in our solar system given here. So I'll try to simplify this diagram. So this model, the model was developed by three scientists, James Casting, Daniel Whitmire, and Ray Reynolds. So a habitable zone, as I said, is not just defined by the distance from the star. It's not just defined by insolation. It's also defined by the atmosphere. So atmosphere එක ගත්තට පස්සේ අපේ habitable zone එකක atmospheric effect කතා කරනකොට අපි කතා කරන්නේ greenhouse gases ගැන. So sun එකෙන් අපේ තරුවෙන් එන සායකෙන් එන solar energy කොච්චර දුරට ප්ලැනට් එකේ ඉතුරු කරගන්න පුළුවන්ද, කොච්චර දුරට ප්ලැනට් එකට මේ සෝලර් එනර්ජි තියාගන්න පුළුවන්ද කියන එක ඩිපෙන්ඩ්ස් වෙන්නේ ප්ලැනට් එකේ තියෙන ඇට්මොස්ෆියර් එක මත. ඇට්මොස්ෆියර් එකේ තියෙන greenhouse gases මත තමයි මේක ඩිපෙන්ඩ් වෙන්නේ. මම හිතනවා ඒගොල්ලෝ දන්නව ඇති කියලා black body radiation ගැන. So for a planet to be habitable, we say it should be away from the moist greenhouse effect. So මම මුලින්ම පටන් ගන්නවා සමා වෙන්න. So අපි habitable zone එකක් ගත්තට පස්සේ planet එකක habitability කියන එක define කරන්න අපි habitable zone එකේ boundaries ටිකක් define කරනවා. So inner boundary එක sun එක පැත්තට star එක පැත්තට තියෙන inner boundary එක අපි කියනවා runaway greenhouse effect කියලා. The runaway greenhouse effect defines the inner boundary of a habitable zone, and the outer boundary is defined by the maximum greenhouse. And the moist greenhouse effect is something that can support life, but it's the very edge of that one. I'll explain that. So runaway greenhouse effect, as I said, here we define planets to be acting as black bodies. Black bodies emit whatever the radiation it absorbs. But in the runaway greenhouse effect, towards the sun, towards the star, from the runaway greenhouse effect, planets cannot radiate all the radiation that it receives from the sun. So හිතන්න planet එකක තියෙනවා ලොකු atmosphere එකක්, greenhouse gases ගොඩාක් තියෙන atmosphere එකක් තියෙනවා. මොකද වෙන්නේ? ඉරෙන් හම්බෙන radiation ඔක්කොම උරා ගන්නවා මේ atmosphere එකෙන්, and the atmosphere heats up. So එතකොට වෙන්නේ මොකද්ද? මේ උෂ්ණත්වය වැඩි වීම නිසා මතු පිට තියෙන වතුර evaporate වෙනවා. මතු පිට තියෙන වතුර වාෂ්ප වෙලා atmosphere එකට යනවා. atmosphere එකට යනවා මේකින් වෙන්නේ මොකද්ද? water vapor කියන්නේ ජල වාෂ්ප කියන්නේ greenhouse gas එකක් විදිහට අපිට consider කරන්න පුළුවන්. ජල වාෂ්ප වලට උෂ්ණත්වය තාපය දරා ගන්න පුළුවන්. So ජල වාෂ්ප නිසා වෙන්නේ මේ atmosphere එක තව දුරටත් රත් වෙනවා. We say it becomes a positive feedback loop. The sun's radiation comes, greenhouse effect is there, and it heats up the atmosphere. So water vapor happens, water vapor forms. So water vapor heats up again. Water vapor keeps heating up the atmosphere to the point that all the oceans in the planet boils away. So liquid water නැති වෙනකන් මේ runaway greenhouse effect එකට star එක පැත්තට තියෙන planets වල උෂ්ණත්වය වැඩි වෙනවා, surface water boil වෙලා නැති වෙලා යනකම්. And we come to the moist greenhouse effect. So for our Earth, the casting system, the James Casting කියන scientist අපේ planet එකට runaway greenhouse boundary එක තියෙනවා 0.84 astronomical units වල. අපේ පෘථිවිය තියෙන 1 astronomical unit away from the sun, but casting puts the runaway greenhouse effect for Earth at 0.84. හැබැයි අලුතින් ආපු models වලින් ඇත්තටම අපි හිතනවා runaway greenhouse for Earth is actually much closer. It can be around 0.95 astronomical units. Then අපි යනවා moist greenhouse effect එකට. මොයිස්ට් greenhouse effect එක රණවේ greenhouse effect එක තරම් බරපතල නැහැ. හැබැයි මොයිස්ට් greenhouse effect එකේදී ජල වාෂ්ප වැඩි වැඩියෙන් හැදීම වෙනවා. හැබැයි මෙතනදි වෙන්නේ ජල වාෂ්ප සම්පූර්ණයෙන්ම පෘථිවියේ තියෙන ජලය ඉවපරේට් වෙලා යන්නේ නැහැ. හැබැයි අපේ පෘථිවියේ සර්ෆේස් එකට තියෙන ළඟම ඇට්මොස්ෆියරික් ලේයර් එක අපි කියන ට්‍රොපොස්ෆියර් එක කියලා මේ මොයිස්ට් greenhouse effect තියෙන ඒරියා එකේදී ඇට්මොස්ෆියර් එක වෝටර් වේපර් වලින් සැචුරේට් වෙනවා. ඒ කියන්නේ ට්‍රොපොස්ෆියර් එක වෝටර් වේපර් වලින් සැචුරේට් වෙනවා. මේකෙන් පස්සේ UV radiation, sun's radiation, you guys know sun emit UV radiation. So UV radiation can photo dissociate water and remove water slowly from the Earth's surface. Runaway greenhouse effect එක වගේ ජලය බොයිල් වෙලා surface එකකින් නැති වෙලා යන්නේ නැහැ. හැබැයි slowly අවුරුදු මිලියන ගණක් පුරා පෘථිවිය මත පිට තියෙන වතුර සෙමින් ඉවත් වීගෙන යනවා moist greenhouse effect එක යටතේ. So moist greenhouse එක effect එක යටතේ ජීවය පවතින්න පුළුවන්. හැබැයි මිලියන ගාණක් අවුරුදු මිලියන ගානකට පස්සේ මේ වතුර සම්පූර්ණයෙන්ම planet එකෙන් නැති වෙලා යන්න පුළුවන්. So it's the boundary between having life and not having life. So the moist greenhouse limit for Earth in our solar system is said to be at 0.99 astronomical units. එච්චර දුරක නෙමෙයි තියෙන පෘථිවිය තව පොඩ්ඩක් ඉර පැත්තට වුණා නම් ජීවය මේ වෙනකොට නැති වෙන්න පුළුවන් පෘථිවියේ. අපි ඉන්නේ 1 astronomical unit away from the sun, so 0.99 astronomical unit is the moist greenhouse effect for our Earth in our solar system. Then there's maximum greenhouse. Maximum greenhouse is the outer edge of the habitable zone. Maximum greenhouse is the limit that greenhouse effect can heat up the atmosphere enough to have liquid water without freezing the water on the surface. So maximum greenhouse එකෙන් එහා තියෙන planets වලට greenhouse effect එකක් තිබ්බත් surface එක atmosphere එක රත් කරන්න හැකියාවක් නැහැ ද්‍රව ජලය තියෙන තාක්කල්. greenhouse effect එකක් තිබ්බත් උෂ්ණත්වය මදි ද්‍රව ජලය තියෙන. So all the liquid on that surface will be frozen. ඒක තමයි basic idea එක. habitable zone එකක ටිකක් complex, you might not have understood, but you can understand what's happening. You can refer. So as I said, I'm just giving you starting points. You can start from here and read about this yourself. So this is a bit of a complex habitable zone definition for planets, all exoplanets and the planets in our solar system. So, okay, so then there's a habitable zone. We can define habitability. So using habitability, defining habitability, we introduce some indexes to find the habitability of a planet. අපි ඔයගොල්ලෝ දන්නවා එක එක missions තියෙනවා, Kepler missions. අපි exoplanets හොයනවා. ඒ කියන්නේ පෘථිවියෙන් අපේ planetary system එකෙන් අපේ solar system එකෙන් එළියේ තියෙන planets හොයන්න missions ගොඩාක් තියෙනවා. ඒ planets වලින් ඒ missions වලින් හම්බෙන planets habitable ද කියලා බලන්න. ජීවය පවතිය හැකි සුළුද කියලා බලන්න අපි indexes ටිකක් define කරනවා. ගොඩක් ඒවා තියෙනවා. මම මෙතන දෙකක් ගන්නවා. Earth similarity index and statistical likelihood of exoplanetary habitability. So Earth similarity index කියන එක habitability කියන අපේ insolation, escape velocity කියන ඒවට අමතරව atmospheric pressure and how rocky they are and energy equilibrium කියන එක consider කරනවා. Earth similarity index කියන එක define කරන්න. So Earth has one Earth similarity index and there are some exoplanets. KOI 9131, TRAPPIST is a very popular one. It was very popular when it was discovered. So මේවට අපි habitability index එකක් දෙනවා. එකට ලං වෙන්න අපි කියනවා these planets have a likelihood of having Earth-like life. If the habitability index is closer to 1, we say these have a high probability of having Earth-like life. So statistical likelihood of exoplanetary habitability index, very popular with, I think, NASA scientists. So they consider magnetic field and gravity also in addition to insolation and escape velocity of a planet to define the habitability. So Earth again has one and Kepler 186f have 0.98 habitability index. This Kepler planet was also very uh, popular recently. තව එකක් තියෙනවා ඔයගොල්ලෝ මං හිතන්නේ අහලා ඇති Kepler not Kepler K218b කියලා planet එකක් ගොඩක් recently හොඳටම කතා කරා. මොකද මේ planet එකේ අපි හොයාගත්ත dimethyl sulfide කියලා gas එකක්. So habitability is the very basic of habitability indexes are the very basic of looking for extraterrestrial life, but that's not everything. If we consider a planet to be habitable, then we look for other things. So habitability index is the first, then we use various other methods, spectrophotometry and everything to find clues for life in those planets. So one thing is the atmospheric composition, gases in the atmosphere. So scientists found dimethyl sulfide in the atmosphere of K218b, and that gas is known to be produced only by life. So K218b has some gas organic compound that can only be produced by life. So ඔයගලුන්ට refer කරලා බලන්න පුළුවන් K218b කියන planet එක exoplanet එක dimethyl sulfide ගැන. So when the scientists first published that they have found evidence for life, I think he was an Indian scientist, so there was a lot of discussion in the scientific community that this is wrong, and they did the experiment again and again in a broad aspect, and they proved again and again that they have discovered evidence, definitive evidence for dimethyl sulfide in the planet. So there's a good chance that it has some kind of life, maybe Earth-like life, but nothing is sure when we talk about astrobiology. So there's that. So we have habitability, we have planets, exoplanets, but how possible it is to find life outside of Earth. So possibility of finding life. So I think that is the most popular idea in astrobiology. So there are 1800 billion stars in the Milky Way galaxy, and the estimate is these 1800 billion stars have 3.2 trillion planets. And 10 billion of these planets are assumed to be terrestrial planets. So to have Earth-like life, as I said, carbon is the building block. So to have carbon, the planet surface should be rocky. So rocky planet comes there, the carbon fundamental unit comes there. So the planet should be rocky to have Earth-like life. I am emphasizing that term again and again, Earth-like life. So 10 billion terrestrial planets, and 300 million of those are in the habitable zone of their planetary system. So, which is a very, very big number. So there's a very good possibility of finding life out there in our galaxy. So 300 million chances of finding life in within our Milky Way galaxy. But the problem is we have, except for the dimethyl sulfide, which was very recent, we have no evidence for life elsewhere. What can be the reason? So this is the most important part, the part I want you guys to go through, read about, because everyone says. So I think most people, when we talk about astrobiology, astronomy, comes to this point and stops there. But I like to go a little bit further and change your ideas a little bit. And I'm not trying to, but after the end of this lecture, I think you guys are going to lower your expectations about finding life outside of Earth within our Milky Way galaxy. Let's see how it goes. So habitability, so planet එක habitability zone එකේ තියෙනවා නම් there's a possibility of life. Is that all? I don't think so. So just because a planet is in the habitability zone of a planet doesn't mean the planet is habitable. So there are other reasons to limit life on a planet. So habitability zone was for a planetary system. So there's a galactic habitability zone also. Galactic habitability zone is defined by the position of a planetary system within the galaxy. So too close to the galactic center, there's a lot of stars, there's a lot of gravitational, intense gravitational effects, lot of stars, supernovas. So the disturbances are too high for the existence of life. So we say galactic habitability zone is the intermediate part of the galaxy. It is not too close to the center of the galactic too close to the galactic center, and not way too away from the galactic center, because I don't know if you guys know. So outages of the galaxy has stars with low metallicity. So in astrobiology, we actually consider all the elements after hydrogen and helium to be metals. Even oxygen, nitrogen, we say as metallic elements in astrobiology only. So stars away from the very far away from the galactic center has the low metallicity. They don't have enough heavier elements, rocky elements, to give rise to Earth-like life. So galactic habitability zone is defined by the density of stars within the neighboring area. So too close to the center, there are too many stars, too many supernovas, quasars, whatever you name. There's a lot of activity in the center, so there can't be life, Earth-like life in the center. Too far away from the center, there's no metallic elements to give rise to the Earth, to rise to life. So it should be in the middle. And just having a planet inside this zone is not enough. If you consider our planetary system, it's not in a major arm of our galaxy. It's not in a major spiral arm of the Milky Way galaxy. It's in a uh, minor arm we call a spur, Orion spur. Our galaxy is in the Orion spur. So again, if a planetary system is within the major arms of a spiral galaxy, there can be perturbations, there can be interferences from neighboring planetary systems, stars, supernovas. So the sun, our planetary system, is in a very convenient position in the galaxy. So we start with 300 billion, if I remember correctly, yes, 300 million habitable planets. So I think you can yourself can decrease the amount, start from the 300 million and find a number between, like reduce, go down from that number with each of these factors. So galactic habitability zone limits the amount of planetary systems that can have life. That's not it. So then that's just not it. Then there's magnetic field. So galactic habitable zone. So you have a habitable zone we have planets in habitable zone, and it's in a in the conducive galactic habitable zone. That's not enough. We have to have a magnetic field in a planet, because solar radiation can sweep away the atmospheric gases in the planet's atmosphere with a effect called sputtering. So solar energy can essentially knock off gases in the atmosphere. Solar radiation, solar winds, පුළුවන් atmosphere එකේ තියෙන gases ගහලා අයින් කරන්න, planet එකෙන් අයින් කරන්න, atmosphere එකෙන් අයින් කරන්න. So magnetic field provide a shield against solar radiation. So a planet's magnetic field is formed. To have a magnetic field, a planet should have a liquid core, and it should have enough rotational speed. So liquid core එක අපේ planet එකේ outer core, and the inner mantle is liquid with enough metallic elements. So our planet has a nice, a strong magnetic field to prevent the atmosphere from getting eroded from solar radiation, so it can have a constant atmosphere around the Earth. අපි ගත්තොත් Mars වලට magnetic field එකක් නැහැ. So from the beginning, from the formation of the Mars, since the formation of the stars, solar radiation has sputtered, has knocked off, eroded Mars atmosphere. So Mars doesn't have a proper atmosphere, because it doesn't have. One of the reasons is because Mars doesn't have a magnetosphere, so magnetic field. So Aspera instrument, there's an instrument installed in Mars called Aspera. It has shown that the red planet, the Mars, is still losing is in its atmosphere because of solar sputtering. අපි ගත්තොත් Venus doesn't actually Venus again doesn't have a magnetic field, but it has a very heavy atmosphere because carbon dioxide is a heavy gas and it's not affected by the solar sputtering effect. So අපට habitable zone එකේ planet එකක් තියෙන්න ඕන, galactic habitability zone එකේ තියෙන්න ඕන, magnetic field එකක් තියෙන්න ඕන. තවත් ඕන අපට tectonic plates. Tectonic plates කට්ටිය හිතන්නේ දෙයක්. Tectonic plates is a thermostat. It regulates temperature, the surface temperature, like the greenhouse gas does for the atmosphere. Tectonic plates operate karma, one of the only geological cycles that can operate without life. This is called the carbonate silicate cycle. I'm not going much into details, but over long time periods, this carbonate silicate cycle can regulate the surface temperature through negative feedback. So surface එක රත් වෙනවා නම් ඒක react කළා, you can refer this, ඒකට react කළා surface එක cool කරන්න පුළුවන්, cool වෙනවා නම් surface එක ආපහු negative feedback loop එකකින් surface එක රත් කරන්න පුළුවන්. So carbonate silicate cycle operates because of the tectonic plates. So we need tectonic plates to have constant surface temperature. So again, that limits. So not all planets have tectonic plates. No other planet on our solar system has tectonic plates. Earth is only planet with tectonic plates. So tectonic plates again limits the probability of finding Earth-like life in our solar system. Then inclination of axis of a planet, which is, I don't have to go for details, I think. So the inclination of axis determines the seasons. So Earth is at a 23.5 inclination, which is very, very convenient. There are very mild, very convenient seasonal changes. If you take Uranus, Uranus will have extreme summers for one hemisphere and extreme winter for one hemisphere. Venus, you won't have you won't essentially have seasons, and we say as biologists, season has been an essential factor for the origin of life and evolution of life. So inclination of axis, I'll go a little bit fast from here on because the time is up, I think. Yeah, but I hope I can take a few minutes. So the fifth factor is celestial shields. So as you probably know, Moon is a very unnatural natural satellite for a planet. Our Earth has a pretty big moon. So Moon and Jupiter. So Moon protects Earth from meteorites, from space debris, and Jupiter, as you can see in this animation, Jupiter keeps objects coming from the Kuiper belt towards the sun in an orbit. There are Trojan asteroids. You can refer Trojan asteroids, and as you can see shown here in pink, it maintains asteroids in an orbit without letting them fall into the inner solar system. In the inner solar system, Jupiter is a very strong, with a heavy gravitational field. It keeps material, space debris, asteroids, everything from falling into the inner solar system. It essentially acts as a shield. So for the formation of life, for the existence of life, continuation of life, there shouldn't be any major hazards happening in the planet. So asteroid, as you know, dinosaurs were wiped out because of asteroids. So these things shouldn't happen regularly. So Jupiter and Moon essentially acts as a shield to protect Earth. So actually, recent investigations, recent research actually says Jupiter's shielding effect is working in opposite. So there was a controversial study that says Jupiter is actually attracting objects in Kuiper's belt towards the inner solar system. I don't know. I'm not an expert on that. There can be, you will see what happens in the future. But for now, we say Jupiter acts as a celestial shield to protect the inner solar system from space debris. And then finally, there are biological barriers. So if you look at this, the animal on the right corner, the horseshoe crab has retained in the same form for 400 million years unchanged. So then there's bacteria, There's dinosaurs. Dinosaurs have been the scientific term for dinosaurs, all kinds of dinosaurs is Archosauria. So Archosauria has existed for 165 to 180 million years. Even if there's life, the possibility of Earth-like life is very unpredictable because biological barriers, because evolution is not a directional process. I'm not going to go much into details, but if you take uh, the Earth's life, the geological time period of Earth as a single day, humans would have existed in the last second only. So we have existed in this earth for a very minute time. So even if there's life, there's a even less possibility of finding intelligent life like ourselves, which brings me to my next section. Before I go to my next section, I'll recap. So there are 300 million planets in our habitable zone, but galactic habitability zone, magnetic fields, plate tectonics, biological barriers, and celestial shields, and other factors also. Atmospheric composition, as you know, Venus has a great atmosphere, but it's carbon dioxide, which cannot support life. Then we say aluminium 26 isotope composition. So aluminium type 26 composition in the solar system during the formation of the solar system also determines the formation of planets. So if the aluminium 26 composition is too high in the protoplanetary disk, so the gas giants might not form. So if there are no gas giants, there are no celestial shields, and life may not form on the terrestrial planets in the habitable zone. So there are other factors, as you can see. We started with 300 million planets, but because it needs other factors, the probability of finding life is very, very low. Uh, I like to think, it's my opinion, I like to think considering all these factors, all these things lowers the probability of finding life. If you get a rough calculation, we'll end up with like 100, about 1 million habitable planets in the solar system, which can accept the biological barriers up to the celestial shields. If you look at the probabilistic values, I'm not going to give you the probabilistic values because I didn't get them from good sources. So what my calculation was then we about 1 million habitable planets in our galaxy, and what we like to say is there's one in a million chance of finding life. So Earth can be actually the only planet with life in our galaxy. When we consider all these kind of uh, possibilities, requirements for life, Earth-like life again, uh, there's a possibility that Earth is actually the only planet with life in our galaxy, which is quite a controversial idea, but you can think about that yourself. In the galaxy, but in the universe, there's a very high possibility that there's life out there in the universe, but in the galaxy, all these barriers limit the uh, probability of having Earth-like life. So then biochemical evolution of life, go a little bit, I will go through these slides a little bit faster because this is basic biology. So for there to be life, there should be genetic material, catalysts, and even if we have all these things, there is a very slight chance of having life. Uh, yeah. So if we consider life forms, why do we look like this? Because of our evolutionary ancestry. The intelligent life on Earth, us humans, look like this bipedal, erect posture, uh, big brain, because of our evolutionary ancestry. Our evolutionary ancestry is from apes, so we look a little bit like them, but, and like the popular scientific community, science fictional community assume intelligent life outside of our world, if there is intelligent life, would look like ourselves. Is this the case? Should life look like us? Uh, I hope you guys can hear me. Can you guys see me? Can someone update me? Okay, so yeah, my headphones died.
Sorry about that. So should sentient life look like us? Question, yes or no? A very quick answer in the chat to see if you guys are asleep or not. No. So sentient life doesn't necessarily have to look like us. It can look like any form depending on the evolutionary ancestry. These are very popular aliens from some movies and cartoons. Evolutionary ancestry is a good factor for sentient life, the main factor, so it doesn't necessarily have to look like us. So I'm actually deviating from my main topic, life outside of Earth, and I'm coming to discuss a little bit about sentient Earth, intelligent life out of Earth. So if you're looking for intelligent life, we don't necessarily have to look at life that looks like us. These can be life that looks nothing like us because of their evolutionary ancestry. So when we talk about evolutionary ancestry, intelligent life, non-Earth-like life comes to the equation. So as I said, there are three fundamentals we look at: elemental composition, solvent, and energy source. So our elemental composition is carbon. It can be silicon because it is the closest thing, as you can see in the periodic table. It's the uh, down the uh, periodic table, that is the next element, carbon silicon. So silicon is the closest thing we can have as a carbon substitute. So elemental composition, there can be life uh, based on silicon. There are research going on. There's research published based on the possibility of having silicon-based life. And solvents, if you talk about the main liquid on our Earth is water, but it doesn't necessarily have to be water. It can be ammonia, it can be methane. So, planet, Saturn's the biggest satellite, natural satellites, Titan, has pools of lakes of liquid methane, ammonia or methane. So the solvent can be different and the energy source can be different. So we extract energy from solar radiation. Other life forms might extract energy from pressure, atmospheric pressure, or magnetic field of the planet. We don't really know. We can't guess. These are just assumptions. So the possibilities are endless. But as I said in the beginning, we can think about this for days and days. So we don't do that. We look for Earth-like life. So as the final section of my lecture, I'll talk a little bit about sentient life because it is a very popular topic when we talk about astrobiology, even if it's not essentially astrobiology. Astrobiology is all kinds of life, not just in intelligent life. But when we talk about intelligent life, Professor Frank Drake comes to the equation. So Frank Drake was an astrophysicist and astrobiologist. So he published a probabilistic equation for finding intelligent life in the galaxy, in the Milky Way. So you can go through these terms. So rate of formation of stars is R, planetary fraction of stars in the planetary system, with planetary systems. So out of these planets, how many planets can be suitable for life, which is all I discussed so far. Then FL is where life actually is there. Then FY is where intelligent life is there. So FC, where they can communicate, and so on. So in astrobiology, this is a very probabilistic equation, very close to science. Not, this is a combination of science fiction and science, I would say, arguably, yes. But in astrobiology, we draw the line at FL. The first four terms are relevant to us. So R, FP, NE, and FL. In astrobiology, we can actually find probabilistic values for these. So in recent years, with the finding of dimethyl sulfide, we are actually approaching the FL terms also. Other than that, for now, all the probabilistic values are for these first three terms: rate of formation of stars, with planetary systems, and with environment suitable for life. So astrobiology revolves around these first three terms, but with the modern technology, we are actually approaching the FL term also. So that is the Drake equation. We can't talk about astrobiology without talking about Drake. Then I will go to some not really scientific, not much scientific, not pseudoscience, but not the core astrobiology. We'll talk about some possibilities of intelligent life out there. So you might have heard about Fermi's paradox. Enrico Fermi, very popular scientist, famously asked in a conversation in 1950, where is everybody? So forget that the very less probability of finding life in the galaxy. Say there's intelligent life. So if there's intelligent life, there's a possibility of having intelligent life. If there's intelligent life, where is everybody? So there's a vast number of stars in the, his argument was that there's a vast number of stars in the galaxy and there's high probability of life during those times. We thought there's high probability of life in 1950s, but there's no contact. So the solutions, the popular solutions for Fermi's paradox is that the civilizations are too far apart. One possibility is civilizations are too far apart, can be on the other sides of the galaxy. So those are not, we can't actually detect the galaxies, and they might approach one point. I think this is very popular in social media. So they might keep developing, and approach a point that they undergo self-destruction, maybe climate change. We don't know. So these are just assumptions. These are just things that scientists like to discuss. Not very doesn't have a good scientific basis, but it's not pseudoscience either. So they might be not using detectable technologies. So these might be having intelligent life, but have not progressed to have detectable technologies from other civilizations, and we might simply not looking correctly. So it might not be like the life we expect, so we don't know to look. So there's a popular popular solution for Fermi's paradox called dark forest hypothesis. This is actually arising from a popular book trilogy, science fiction trilogy. You might have seen the Three-Body Problem. There was a TV series also. So this is the second book of Three-Body Problem, the dark forest hypothesis. So in this hypothesis, which is actually talked in scientific community also, in this hypothesis, we assume that the galaxy to be a dark forest. So every civilization is a hidden hunter striving to avoid detection. So in the dark forest, survival is the most important thing. ජීවත් වෙන එක තමයි ප්‍රධාන දේ. And we don't know if other civilizations have other intentions, like mining other resources. We don't know their intentions. They might have good intentions, bad intentions. We don't know. And if they detect other civilization, there's a possibility that they assume the worst. They assume the worst, and they destroy the other civilization. So they use silence as a strategy. If there are intelligent civilizations out there, the dark forest hypothesis says that they are remaining silent and undetectable to prevent any preemptive strikes. So this is a very popular, very nice discussion to have about Fermi's paradox. This is not the only thing, but it's a very nice thing to have. You can look for yourself. You can read about that self. So this is arising from actually the three-body problem. This is the second book, if I remember correct. Dark forest hypothesis is in the second book, but this is a good solution for Fermi's paradox. Why, if there's intelligent civilizations out there, why they are avoiding detection? So as a final note, I would like to say Earth is a very peculiar system. If you look at all the factors that support life, it's a very, very astronomically very rare case. It's very stable. There's no very drastic changes happening. It's a very balanced and a balanced state in in the solar system, in our Earth. It's a very rare case in planetary systems. So very rare occurrences, even in astronomical scale. So there's a chance that we might actually be the only life on our galaxy, which is very, very contrasting idea from the popular belief. But yeah, so you have to think about that. We usually say, okay, there's good possibility that there's life out there. There is a good possibility, even if it's less than that possibility, there's a possibility that we might be the only life in our galaxy. In the universe, there is a very good possibility there's life, but in our galaxy, we might be the only life there is. So with that, I would like to end my lecture. I took a little bit more time. So these are the references I use. You can maybe take a picture. So I took my facts from these books. These are 4 very popular astronomy textbook. So yeah, that's the end of my lecture. I hope you guys enjoyed. Might have been a little bit complex than you expected, but I hope you guys got the general idea. Yeah, thank you very much for listening. If you have questions, very quickly you can ask in the chat. Again, I'm not an expert. I'll try to answer the best I can. Yeah. Yeah, I will stop sharing my, yes. Yeah, so I hope you guys enjoy. If you have questions, you can put in the chat. Yeah. Sorry about taking a little bit more time than expected. I will try to answer your questions the best I can. Again, this was a very basic, very fundamental points of astrobiology with a bit of a controversial idea at the end. You might not agree with me, you might agree with me. There's a good possibility. You might not agree with me, but yeah, think about that. So if you have questions, you can ask. Otherwise, we can proceed with the plan. Yes, Tishak, yeah. Yeah. So I have a question. So apart from the books you referenced, other books can you recommend? So as a starting point, usually all kinds of astronomy textbooks have a section of astrobiology. Astrobiology textbooks are a little bit advanced. They go to astrophysics, biochemistry and molecular biology. So astrobiology books are mostly biochemistry and astrobiology. So you can start from, if you are a beginner, you can start from general astrobiology astronomy textbooks. I don't actually know about other astrobiology textbooks, but you can just Google and find out. Usually textbooks, recently published textbooks are a good place to start reading. I'm not sure about the exact topics other than that. Yeah. Yes. I'm not seeing any other questions.
Thank you, sir, for this enlightening session. It was truly fascinating to learn about this very unique field, and I'm sure all the participants learned a lot of valuable things today. Before we move to the end of our session, I would like to kindly request everyone in this session right now to kindly switch on your web cameras and join us all for a commemorative group photo.
Yeah, so I have one question. I think a pretty interesting question. I am doing medicine. How can I get a path in this? So I'm not an astrobiologist. My field is related to astrobiology as molecular biology, but you can always refer books, study yourself. I studied myself, so there's no limitation. Even if you're doing physics, maths, engineering, whatever, it doesn't matter. You can read yourself, and yeah. If you want to join astrobiological research, if you want to be a scientist in astrobiology, you can always talk to people. If you can always text email scientists. So I am actually going to work with an astrobiologist for my PhD, not really an astrobiology PhD, but I am going to work with an astrobiologist. So you can always refer and email them saying I'm interested in this field, what are the opportunities I have. So there's no limit for the future with what you do now. It's all about what you can do. You can read yourself and explore the possibilities. Yes. Thank you.
Thank you so much, sir. So now I would like to kindly request everyone to switch on their web cameras and join us all for a commemorative group photo.
I think everyone can turn on the cameras just for a quick photo.
Thank you all so much. Now, I would like to take a moment to express our heartfelt gratitude to everyone who helped make today a resounding success. First and foremost, a big thank you to Mr. Sathira Deegala for sharing his valuable insights and guiding us through the intriguing world of astrobiology. Your passion and knowledge have truly sparked all of our curiosity and inspired us to look at the universe in a very different and new lens. Also, to the organizing team at the Astronomical Society of the University of Colombo, thank you so much for making the first session of Meissa 2.0 a resounding success. And finally, to each and every one of you who joined with us here this evening, despite the troubling weather conditions as well, I may add, we would like to thank you all so much for being a part of this journey, and we are so grateful that you were able to join. We also look forward to seeing you in our upcoming sessions as well. Until then, keep wandering, keep exploring, and always look up at the night sky and wonder. Have a great night. Thank you so much.